Hello there, and welcome to the Sleep with Science channel, where tonight we are going to drift together into the deepest, most breathtaking silence you have ever known. A silence so vast, so complete, so incomprehensibly ancient, that the moment you begin to feel it, something inside you will quietly let go. So find your position now. Let your body sink into whatever is beneath you. Feel the weight of the day dissolving, vertebra by vertebra, breath by breath. And as your eyes grow heavy and the world around you begins to soften at its edges, allow your mind to travel somewhere it has perhaps never truly gone before, not just to space, but into it. Into the real thing. Not the space of science fiction, not the glittering playground of movies and imagination, but the actual, honest, staggering truth of what lies beyond this fragile blue world we call home. Because here is what most people never stop long enough to feel. Space is not the beautiful backdrop we have been taught to admire from a comfortable distance. It is something far more profound than that. It is the universe in its most unfiltered, most sovereign, most honest form, and it operates by rules that have absolutely nothing to do with human comfort, human survival, or human existence at all. Right now, as you breathe slowly and your heartbeat begins to find its quiet rhythm, consider this. The International Space Station, humanity's most extraordinary outpost beyond Earth, orbits our planet at roughly 17,500 miles per hour. The astronauts aboard it, these remarkable human beings who have trained for years, who carry with them the absolute best of what science and engineering can offer, they are separated from the vacuum of space by a wall averaging just a few inches thick. A few inches of metal and insulation and engineering brilliance standing between living, breathing human beings and an environment that would, without a single moment of hesitation, end those lives in ways both swift and incomprehensible. And yet, even knowing this, most of us have never truly felt the weight of what that means. We see photographs of astronauts floating serenely, smiling behind their visors, the Earth glowing blue and white and impossibly beautiful in the background, and something in us relaxes into a sense of wonder that never quite tips into awe. Never quite tips into the deep, reverent understanding that what we are looking at is not a triumph over space. It is a careful, fragile, breathtaking negotiation with it. Space does not hate us. That is important to understand as your body continues to soften and your breathing deepens and the room around you grows distant and quiet. Space does not hate us because space does not feel anything at all. It is indifferent in a way that no word in the English language was ever quite designed to capture. It is indifferent the way mathematics is indifferent. The way gravity is indifferent. There is no malice in it, no intention, no awareness of our smallness or our courage or our extraordinary desire to reach beyond our atmosphere and touch the dark between the stars. There is only the vacuum, the radiation, the silence, the cold that does not creep but simply is, a cold so absolute, so deeply settled into the fabric of the universe that in the shadow side of space, temperatures can plunge to nearly minus 455 degrees Fahrenheit, just a whisper above absolute zero, the theoretical point at which all molecular motion ceases entirely. The point at which the universe itself, in a sense, goes still. And then there is the light side of that same reality, because space is also a place of extraordinary, unrelenting heat. In direct sunlight, with no atmosphere to diffuse or moderate the energy of our star, temperatures can surge to over 250 degrees Fahrenheit. A swing of more than 700 degrees between shadow and sunlight, sometimes across a distance of just a few feet. Human skin exposed to that environment unprotected would not simply burn or freeze. It would face both simultaneously, depending on the angle of the sun, the rotation of the body, the geometry of the moment. A spacesuit, then, is not a costume. It is not equipment in the way we use that word for things like helmets or harnesses. A spacesuit is a miniature spacecraft, engineered to regulate temperature, maintain pressure, supply oxygen, remove carbon dioxide, protect against micrometeorite impacts, shield against radiation, and allow a human being to move, to work, to think, to survive, all at once, all continuously, in an environment that was built by the universe for no one. That was built, in the truest sense, for nothing at all. Breathe that in slowly now. Let it settle behind your eyes, behind your sternum, somewhere deep in the quiet center of your chest. Because what we are beginning tonight is not simply a recitation of facts, as astonishing as those facts are. What we are beginning is something more like a feeling. A slow, meditative unfurling of what it actually means to exist in a cosmos that is, in nearly every measure, hostile to the very chemistry that animates you right now. The oxygen in your lungs, the warmth beneath your skin, the soft electrical pulse of the thoughts dissolving gently at the edges of your mind as sleep begins to reach for you. You are, in this moment, the universe's most unlikely creation, fragile and warm and conscious in a cosmos that is cold and vast and silent beyond any scale the human mind was designed to truly hold. And perhaps that is where the real wonder lives, not in the danger itself, but in the extraordinary improbability of your being here at all, breathing and aware and capable of contemplating the very forces that would, without this thin shell of atmosphere and gravity and magnetic protection, dissolve you back into the stardust from which you came. Let that thought carry you gently now, like a current beneath deep water, slow and inevitable and strangely peaceful. Because before we can truly feel the weight of what space asks of those who dare to enter it, we need to understand something foundational. Something that most science classes brush past in a sentence or two, but that deserves to be held carefully, turned over in the hands of the mind, examined the way you might examine something ancient and irreplaceable. And that is simply this: the Earth is not just our home. It is our life support system. It is the single most sophisticated survival apparatus in the known universe, and it has been running, quietly and continuously, for approximately 4.5 billion years without a single moment of interruption. Right now, without any effort from you, without any awareness on your part, the Earth's magnetic field is deflecting a continuous stream of charged particles pouring outward from the Sun at speeds of up to 900 kilometers per second. This is the solar wind, and it is not a gentle breeze. It is an unrelenting river of energy and radiation that, if it reached the surface of our planet unimpeded, would gradually strip away our atmosphere the way it has stripped away the atmosphere of Mars, slowly, patiently, over millions of years, until what was once a world capable of holding liquid water and perhaps even life became a cold, thin-aired, radiation-scoured desert of rust-colored rock. But it does not reach us. Because wrapped around this planet like an invisible force field drawn from the iron-rich churning of our planet's outer core is the magnetosphere, a magnetic bubble extending tens of thousands of miles into space, bending and deflecting and absorbing the solar wind in a continuous, silent, invisible act of protection so vast and so constant that we have lived our entire lives inside it without ever once having to think about it. Feel your breath slow a little more now. Feel the mattress, the pillow, the warmth of the blanket if there is one. Feel how still your body is becoming. You are, in this moment, held. You are held by gravity, by atmosphere, by magnetic fields, by 4.5 billion years of planetary evolution that conspired, through processes no one fully planned and no one fully understands, to produce exactly the right conditions for exactly the kind of life that can lie in a warm, dark room and think about stars. Astronauts leave all of that behind. The moment the engines of a rocket ignite and the vehicle begins its climb through the atmosphere, the process of separation begins. Not just physical separation from the ground, but a gradual, stage-by-stage departure from every single layer of protection that this planet has spent billions of years building around us. The thick lower atmosphere, where pressure is sufficient to keep the gases in your blood dissolved properly, thins and fades. The ozone layer, which absorbs the ultraviolet radiation that would otherwise damage DNA at the cellular level with every moment of sun exposure, is left below. And then the magnetosphere itself, while still offering some protection in low Earth orbit, become something to be navigated rather than simply inhabited, because the radiation environment even in low Earth orbit is measurably, significantly different from what it is on the surface. The International Space Station orbits at an altitude of roughly 250 miles above the Earth's surface. That sounds like a long distance. And in human terms, in the terms of roads and walking and even flight, it is. But in the terms of the magnetosphere, it is still relatively close, still relatively sheltered. Astronauts aboard the station receive radiation doses approximately 10 times higher than what a person living on the surface would receive in the same period of time. 10 times. And that is in a relatively protected orbit, inside a shielded structure, with careful monitoring and strict time limits on extravehicular activities. Spacewalks, designed specifically to minimize radiation exposure during periods of heightened solar activity. Now let your mind drift a little further. Not quickly. Slowly. The way a leaf releases from a branch in autumn, not falling so much as simply letting go of where it was. Let your mind drift to the moon. To the surface of the moon, where Apollo astronauts walked between 1969 and 1972, 12 human beings in total, each one of them standing on a world with no atmosphere, no magnetic field, no protection whatsoever from the radiation pouring continuously from the sun and from the cosmos beyond. The lunar surface is bombarded by cosmic rays, high-energy particles originating from supernovae and other violent events across the galaxy, at levels that would, over extended periods, represent a serious long-term health risk to any human being living or working there without significant shielding. And yet they went. They descended the ladder. They placed their boots on the gray powdered regolith. They looked up at the Earth hanging in the black sky above them, blue and white and heartbreakingly beautiful, a marble of light suspended in a darkness so absolute it seemed less like a color and more like the absence of everything, and they carried out their work with a calm professionalism that, when you sit with it quietly in the dark, feels almost impossible to fully comprehend. Because what they were standing in was not simply another landscape. It was not a foreign country or an unfamiliar terrain. It was a fundamentally different category of place. A place where the rules that govern survival on Earth do not apply. Where the assumptions your body makes every moment of every day, that there is air to breathe, that pressure surrounds you evenly, that the temperature will remain within a range your biology can manage, that the ground beneath your feet is not quietly irradiating you from below. Every single one of those assumptions becomes, without the technology wrapped around you, a fatal error. The moon's surface temperature swings between approximately 260 degrees Fahrenheit in direct sunlight and minus 280 degrees Fahrenheit in shadow. And unlike Earth, where the atmosphere acts as a great thermal buffer, absorbing, distributing, moderating heat so that even the most extreme surface temperatures on our planet remain within the range of liquid water, the moon has no such buffer. The transition between those extremes can happen across a distance of inches. Step from sunlight into shadow and the temperature of the surface beneath your boots drops by hundreds of degrees nearly instantaneously. The Apollo spacesuits were engineering marvels, layered systems of materials and mechanisms designed to manage exactly these extremes. They weighed approximately 180 pounds on Earth, though of course on the moon, where gravity is roughly 1/6 of Earth's, they felt considerably lighter. But they were still cumbersome, still limiting, still a constant reminder that the human body was being kept alive by technology rather than by the natural generosity of the environment. And here is something worth holding gently in your mind as your breathing continues to deepen and the world around you grows softer and more distant. Those suits, those extraordinary suits, were pressurized to only about 4.3 pounds per square inch. For context, the atmospheric pressure at sea level on Earth is approximately 14.7 pounds per square inch. The suits maintained a pure oxygen environment at that reduced pressure, which allowed astronauts to move with somewhat greater ease than a fully Earth pressure suit would have permitted. But it also meant that those suits were, in a very real sense, balloons. pressurized containers holding a bubble of breathable atmosphere around a human body in a vacuum. A single significant puncture. A single critical seal failure. And that bubble ends. Let that settle quietly. Not with fear, because fear is not what this journey is for. Let it settle with something more like reverence. A deep, slow, bone-level appreciation for the extraordinary courage and extraordinary engineering and extraordinary human determination that made those footsteps on the lunar surface possible at all. Because this is one of the most remarkable things about the story of human space exploration. It is not a story of conquering space. Space has not been conquered. Space cannot be conquered in any meaningful sense of that word. It is a story of negotiation, of careful, painstaking, profoundly humble negotiation with an environment that holds all the power and extends no quarter and makes no allowances for the smallness or the fragility of the creatures reaching up toward it from their warm, protected, atmosphere-wrapped world. Allow your body to sink a little deeper now. Let your shoulders release. Let your jaw soften. Let the space behind your eyes grow wide and dark and quiet, the way the sky grows when you are far from city lights and you look up and you begin to truly see how many stars there are. There are, in the observable universe, an estimated 2 trillion galaxies. 2 trillion. Each one containing, on average, hundreds of billions of stars. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars, and it stretches approximately 100,000 light-years from edge to edge. A light-year, the distance light travels in a single year, moving at 186,000 miles per second, is approximately 5.88 trillion miles. And the Milky Way is 100,000 of those. The nearest star to our own Sun is Proxima Centauri, sitting at a distance of approximately 4.24 light-years. If you were to travel to Proxima Centauri aboard the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which at its peak velocity travels at approximately 430,000 miles per hour, the journey would take roughly 6,500 years. And in all of that distance, in all of that incomprehensible, mind-dissolving expanse of space between here and the nearest other star, there is nothing. Not empty in the way a room is empty. Not empty in the way a field at night is empty. Empty in a way that has no human equivalent, no earthly analogy that comes even remotely close to capturing it. A vacuum so near perfect that the handful of atoms drifting in each cubic meter of interstellar space represents a density so low it makes the best vacuum chambers ever created on Earth seem crowded by comparison. And it is in this nothing, across these distances, through this radiation and this cold and this silence and this vacuum, that any spacecraft carrying human beings would have to travel to reach even the most modest of destinations beyond our own moon. A journey to Mars, our nearest planetary neighbor and the most discussed destination for future human exploration, would take approximately 7 months one way under current propulsion technology. 7 months of living inside a pressurized metal cylinder roughly the size of a modest apartment, hurtling through interplanetary space at tens of thousands of miles per hour, with no ability to turn around, no possibility of rescue, and no atmosphere, no magnetosphere, no planetary gravity to offer any of the quiet, invisible protections that wrap around you right now as you lie here breathing slowly in the dark. 7 months. And that is just the journey there. Any crewed mission to Mars would require the crew to wait on the Martian surface for approximately 14 to 20 months before the orbital geometry of Earth and Mars aligned favorably enough to permit a return journey. The total mission duration would be somewhere in the range of 2.5 to 3 years. 2.5 to 3 years spent entirely beyond the shelter of Earth's magnetosphere, exposed to the full radiation environment of interplanetary space, relying entirely on the engineering of a spacecraft and a habitat that cannot be repaired from Earth, cannot be replaced from Earth, and must function without failure for the entire duration of that extraordinary, lonely, beautiful, terrifying journey. And radiation, on such a mission, is not a background concern. It is one of the central engineering and medical challenges of the entire endeavor. In interplanetary space, beyond the protection of the magnetosphere, astronauts would be exposed to two primary sources of radiation. The first is solar particle events, sudden, intense bursts of radiation released during solar flares and coronal mass ejections, events in which the sun releases enormous quantities of charged particles that can arrive at a spacecraft with relatively little warning and at levels that, without adequate shielding, could deliver a potentially lethal dose in a matter of hours. The second source is galactic cosmic rays. These are high-energy particles, protons, atomic nuclei, electrons, that originate from outside our solar system, from supernovae, from neutron stars, from the violent, energetic processes of a galaxy in constant motion. Unlike solar particle events, which are episodic and somewhat predictable, galactic cosmic rays are continuous. They arrive from every direction simultaneously, and they are extraordinarily difficult to shield against because the most energetic of them can penetrate virtually any material humanity is currently capable of constructing and carrying into space at reasonable mass. Let your mind rest in that for a moment. Let it settle slowly, the way sediment settles through still water, drifting downward without hurry, finding its place at the bottom of things. There is something almost meditative about the nature of cosmic rays. They have been traveling, many of them, for millions or even billions of years. They were born in the deaths of stars, in explosions so vast and so energetic that for brief moments they outshone entire galaxies. They crossed the interstellar medium, navigating the vast nothing between star systems, riding the subtle currents of magnetic fields woven through the galaxy like invisible rivers. And then, after all of that distance, after all of that time, they arrive here. At this solar system. At this small blue planet. Most of them deflected, absorbed, scattered by the magnetosphere and the atmosphere. But some of them, a small and constant trickle, reach the surface. Pass through the roof above you. Pass through you right now, as you lie here in the dark. You have been passed through by the universe your entire life without ever feeling it. Astronauts on a Mars mission would feel it far more acutely, not as a sensation, because radiation at these levels has no immediate perceptible feeling, but in the accumulating cellular reality of what that exposure does over time. High-energy particles passing through biological tissue do not simply slide through cleanly. They interact. They ionize molecules along their path, breaking chemical bonds, damaging DNA, creating what physicists call a track of ionization through the tissue. The body has remarkable repair mechanisms for exactly this kind of damage, and for ordinary background radiation levels, those mechanisms manage the load with extraordinary efficiency. But as exposure increases, as the cumulative dose rises, the balance between damage and repair begins to shift. The risk of cancer increases. The risk of damage to the central nervous system, the brain, the spinal cord, becomes a concern that researchers are only beginning to fully quantify. Recent studies involving astronauts who have spent extended periods aboard the International Space Station have shown changes in brain structure and cerebrospinal fluid distribution that appear to be related to microgravity and radiation exposure. The ventricles of the brain, fluid-filled spaces within the brain tissue, have been observed to enlarge slightly after long-duration spaceflight, and some of these changes appear to persist for years after return to Earth. The visual systems of some astronauts have been affected, with changes to the shape of the eye and the optic nerve that in some cases have resulted in lasting vision impairment. These are not hypothetical risks or theoretical concerns. They are documented, measured, observed changes in the bodies of real human beings who left this planet and spent time in an environment their bodies were never designed to inhabit. And yet, and here is where the story becomes something more than a catalog of hazards, every single astronaut who has experienced these effects, everyone who has returned to Earth with a changed body and a changed relationship to gravity and a changed understanding of what this planet means, Virtually every one of them has said, in one form or another, that it was worth it. That the view from the cupola window of the International Space Station, that slow blue curve of the Earth hanging in the black, was worth every joint that ached upon return, every blurred edge of vision, every night of disoriented sleep where the body remembered floating and could not quite make peace with the weight of blankets and gravity and the press of a mattress beneath a spine that had briefly, gloriously, forgotten what a spine was for. Worth it. And perhaps that is the most haunting thing about space. Not the silence, not the radiation, not the cold, though we will come to the cold in a moment, and it deserves its own kind of reverence, but the fact that human beings, fully aware of what the void does to the body, continue to lean toward it. Continue to want it. Continue to press their faces against the window of whatever vessel carries them upward, and feel something that cannot be easily named, but sits somewhere between grief and gratitude and a recognition so deep it bypasses language entirely. They call it the overview effect. A shift in perception so consistent across astronauts from different countries, different backgrounds, different languages and belief systems, that it has been studied by psychologists and philosophers alike. The sensation, described again and again in nearly identical terms, of seeing the Earth as it actually is, not as a collection of nations and borders and disputes, but as a single, delicate, luminous object suspended in an incomprehensible darkness. A thin shell of atmosphere. A closed system. The only warmth, as far as the eye can reach, in every direction. And that darkness they are suspended in, let us sit with it for a moment, because it is easy to speak of space as darkness and move on without truly letting that register. The darkness of space is not the darkness of a room with the lights off. It is not the darkness of a cloudy night or a deep forest or the bottom of a stairwell. It is an absence so complete, so structurally total, that it operates by different rules than anything the human eye was calibrated to understand. In the direction away from the sun, in the shadow between stars, the temperature of space, the ambient temperature of the universe itself, the cosmic background temperature that pervades all of empty space like a whisper left over from the beginning of everything, sits at approximately 2.7 degrees Kelvin, which, translated into terms the body can attempt to feel, is roughly negative 270 degrees Celsius. Negative 454 degrees Fahrenheit. Let that number move through you slowly. Negative 454 degrees Fahrenheit. There is no environment on Earth, no natural place, no cave or polar plain or mountain summit that comes anywhere close to that. The coldest naturally occurring temperature ever recorded on the surface of this planet was in Antarctica, hovering around negative 93 degrees Celsius. Brutal. Life-ending within minutes of exposure. And yet that temperature, that record-breaking, skin-crystallizing, lung-collapsing cold of the most inhospitable place on Earth, is warmer than the ambient void of space by nearly 200 degrees. Space is not merely cold. It is the origin of cold. It is what cold is reaching toward when it reaches its furthest possible expression. And yet, strangely, paradoxically, an unprotected human being in direct sunlight in low Earth orbit would not freeze immediately. They would burn. The sun, without the mediation of an atmosphere to scatter and soften its radiation, delivers energy directly and mercilessly to any surface it touches. The temperature of an object in direct sunlight in space can reach over 120 degrees Celsius on the sun-facing side, while the shadow side of that same object simultaneously plunges toward the deep cold of the void. The International Space Station itself cycles through this thermal whiplash every 45 minutes as it orbits the Earth 16 times per day, crossing from blazing light to absolute shadow and back again, over and over, while its thermal control systems work continuously to keep the interior at a temperature where human beings can think and sleep and eat and breathe. The suits that astronauts wear during spacewalks, those brilliant white structures of layered materials that look almost ceremonial, almost like something worn for a ritual rather than a repair, are, in a very real sense, portable planets. They contain their own atmospheres, their own temperature regulation, their own pressure. Without the suit, the human body in open space would face not one threat but several, simultaneously, moving faster than the nervous system could process them. The lack of pressure would cause the moisture in the eyes and mouth to evaporate almost instantly. The dissolved gases in the blood, freed from the pressure that keeps them in solution, would begin to form bubbles in the tissues and bloodstream, a process related to what deep-sea divers call the bends, but faster and with no possibility of treatment. The lungs, if the astronaut attempted to hold their breath, would rupture from the pressure differential. The skin would swell as the body's fluids expanded against nothing. And through all of this, the radiation that streams continuously through the void, the same radiation that accumulates slowly in the bodies of astronauts over months aboard the station, would be delivering its full unmediated intensity to every cell. Consciousness, under such conditions, would last perhaps 15 seconds. Perhaps less. Not because of the cold, which would take far longer to conduct its way through the body's tissues, but because the brain, deprived of oxygen and subjected to the sudden violence of decompression, would simply stop. Not dramatically. Not with the violence the mind imagines when it tries to picture such a thing. But quietly, in the way that all biological processes stop when the conditions that sustain them are withdrawn. A candle does not argue with the wind. It simply ceases. And that stillness, that absence of argument, is in some ways the most accurate metaphor for what space actually is. It does not hate the human body. It does not threaten or menace or pursue. It is simply indifferent in a way that no earthly environment can fully replicate, because every earthly environment, no matter how hostile, exists within the same atmosphere, the same gravity, the same basic physical envelope that produced the human body over billions of years of slow, patient evolution. Even the most lethal places on Earth are, in the deepest sense, home. They are variations on a theme the body understands. Space is not a variation. It is a different kind of existence entirely. A different set of physical laws, not in their mathematics, but in their consequences. And to enter it is to carry your entire world with you, sealed inside a suit or a station, because the moment that seal is broken, the world you carry ends. This is why every gram of material sent beyond the atmosphere is measured and accounted for with a precision that borders on devotion. The oxygen that astronauts breathe aboard the International Space Station is not simply stored in tanks, though some of it is. Much of it is generated through a process called electrolysis, in which water is split into its component hydrogen and oxygen by passing an electrical current through it. The water itself is recycled, captured from the breath and sweat and other biological outputs of the crew, filtered and purified through systems of extraordinary complexity until it is clean enough to drink again. Nothing is wasted. Nothing can be wasted. The station is a closed loop, a tiny biosphere engineered with enormous effort to approximate the conditions of a planet, because the alternative to that effort is the void pressing in from every direction, patient and absolute, and 2.7 degrees above the coldest temperature the universe permits. Think about water for a moment. The way it moves in a glass when you tilt it. The way it pools and flows and finds the lowest point in any container, obedient to gravity in the way that all liquids are, that easy downward pour that the body has understood since infancy. Aboard the station, water does none of that. Released from a container in microgravity, water forms a sphere. A perfect, trembling, iridescent globe that floats in the air of the cabin and reflects the face of anyone who looks at it. Beautiful, astronauts say. Strange, they say. Deeply, unsettlingly strange, in the way that beautiful things sometimes are when they reveal how conditional your understanding of normal has always been. The astronauts drink through sealed pouches with straws. They bathe with wet cloths. They sleep in sleeping bags attached to the wall, because in microgravity there is no down, no up, no natural orientation the body settles into when consciousness releases its hold. Some astronauts report that sleep in space has a quality unlike any sleep on Earth, a floating suspension that is either deeply peaceful or profoundly disorienting depending on the night, depending on the mind, depending on how well the body has adapted to the strange democracy of weightlessness where every direction is equal and none of them is home. And outside the thin hull of that station, beyond the insulation and the pressurized modules and the solar panels turning slowly to track the sun, the cold continues. The deep, structural cold of the universe. Not a weather condition. Not a season. A fundamental property of the space between objects, the thermal truth of emptiness itself. When there is no matter to hold heat, heat does not exist in the way we experience it. Warmth, as the human body knows it, is a relationship between molecules. It is motion, the vibration of particles against each other, the kinetic conversation of matter with itself. In the void where matter is absent, that conversation cannot happen. And so the temperature falls and continues falling until it reaches that number, that 2.7 Kelvin, that whisper-thin margin above absolute zero that represents the last faint warmth of the universe's own ancient light. The cosmic microwave background radiation. That is what that 2.7 degrees actually is. Not a coldness the universe imposes, but a warmth it cannot quite let go of. The afterglow of the Big Bang, stretched and cooled over 13.8 billion years of expansion, still present in every direction, still detectable in the hiss of instruments sensitive enough to listen for it. The universe is, in this sense, still exhaling from its first breath, still radiating the memory of its own beginning. To float in space is to float inside that memory, to be surrounded, on all sides and in every direction, by light so ancient and so diffuse it has become indistinguishable from cold. To exist, briefly and improbably, within a history so vast that a human lifetime, an entire human civilization, registers within it the way a single breath registers against the age of a mountain. And the radiation that fills that space, the cosmic background and the solar wind and the galactic cosmic rays streaming in from distant catastrophic events, supernovae and colliding neutron stars and the churning engines of galaxies far beyond the reach of any telescope we have yet constructed, that radiation does not pause at the edge of the solar system. It does not slow as it crosses the orbit of Neptune, does not dim as it passes through the asteroid belt, does not soften as it reaches the thin blue envelope of atmosphere that wraps this planet like a whispered promise. It travels at the speed of light, because it is light, in the broadest sense of that word, electromagnetic energy moving through the vacuum with a constancy and an indifference that is almost philosophical in its purity. What protects us from it, here on Earth, is a combination of things so elegant in their layering that it is difficult to appreciate them without first imagining their absence. The atmosphere, that thin shell of nitrogen and oxygen and trace gases, absorbs and scatters much of the ultraviolet radiation from the sun before it reaches the surface. The magnetic field, generated by the churning of molten iron in the Earth's outer core, deflects the charged particles of the solar wind, bending their paths around the planet the way water parts around a stone in a stream. Together, these systems create a protected zone, a habitable bubble, inside which biology as we know it became possible. Remove either one, and the surface of the Earth would become something very different. Mars, which lost its magnetic field billions of years ago for reasons scientists are still working to fully understand, subsequently lost most of its atmosphere as well, stripped away particle by the solar wind over geological timescales. What remains is less than 1% of Earth's atmospheric pressure, thin enough that liquid water cannot exist on the surface, cold enough that the average temperature hovers around -60 degrees Celsius, and irradiated enough that any organism accustomed to Earth's surface would face DNA damage at a rate the body's repair mechanisms could not sustain indefinitely. Mars is not the worst case. It is, in fact, a relatively gentle example of what happens to a world without protection. Europa, one of Jupiter's moons, orbits within Jupiter's enormous magnetic field, which rather than protecting it focuses intense radiation onto its surface. The radiation environment at Europa's surface is so severe that an unprotected human being standing there would receive a lethal dose within hours. The ice that covers Europa's ocean, that beautiful, striated, cracked surface that suggests an entire world of liquid water hidden beneath, is itself a product of bombardment, processed and altered by radiation into a chemistry unlike anything found naturally on Earth. And yet beneath that ice, in the darkness of an ocean that has not seen sunlight in billions of years, there may be life. The possibility is not a fantasy. It is a serious scientific hypothesis grounded in what we know about life's relationship with water and chemical energy rather than sunlight. Hydrothermal vents on Earth's ocean floor support entire ecosystems that have never needed the sun, organisms that draw their energy from the chemical reactions between hot water and rock, from the heat of the planet itself rather than the light of the star above it. If that is possible here, in the deep dark of our own ocean, the question of whether it is possible in the deep dark of Europa's becomes not just conceivable but genuinely pressing. This is one of the quiet revolutions in how humanity understands life and its possibilities. For most of human history, the sun was not merely important to life, it was assumed to be the absolute prerequisite, the source from which all biological energy ultimately flowed. Then we found the vents. Then we found organisms living in solid rock, in hypersaline lakes, in the superheated water of geysers, in the intensely irradiated cooling ponds of nuclear reactors. Life, it turned out, is not a fragile exception to the rules of chemistry. It is an expression of chemistry's own tendency, under the right conditions, to become complicated, self-sustaining, and persistent. And if life is that persistent here, on this one world we know, then the universe, which contains more stars than there are grains of sand on all of Earth's beaches, which has been running chemical experiments on planetary surfaces and in subsurface oceans and in the dense clouds of molecular gas between stars for nearly 14 billion years, becomes a place of staggering biological possibility. We have not found that life yet. This is worth sitting with, slowly, in the way that this entire subject deserves to be sat with. We have looked. We have listened. We have pointed radio telescopes at thousands of star systems and analyzed the atmospheres of distant planets for chemical signatures that might suggest biology at work. And so far, the universe has returned only silence. But silence is not the same as emptiness. A forest at 3 in the morning is silent to someone standing in a clearing, and yet it is alive in every direction, in ways that will not reveal themselves until the light changes. The universe is, in cosmic terms, a forest we entered moments ago. Our radio transmissions, the earliest of which have been traveling outward from Earth for just over a century, have reached a sphere of space containing perhaps 10,000 star systems out of the 200 billion in our galaxy alone. We have introduced ourselves to a neighborhood so small, relative to the whole, that calling it a neighborhood is almost generous. The Drake equation, that famous attempt to estimate the number of communicating civilizations in the galaxy, was never meant to provide an answer. It was meant to organize ignorance, to lay out clearly and honestly every factor we do not know, every variable we cannot yet measure. Frank Drake, who wrote it in 1961 as a framework for the first scientific conference on the search for extraterrestrial intelligence, understood that the equation's value was not in its solution, but in its questions. Each variable in that equation is a door, and behind each door is a field of inquiry large enough to occupy entire generations of scientists. What fraction of stars have planets? What fraction of those planets are capable of supporting life? What fraction of those actually develop it? What fraction of life becomes intelligent? What fraction of intelligent life develops technology? What fraction of that technology produces signals detectable across interstellar distances? And finally, the one that carries the most weight in the quiet hours, the one that settles into the mind like a stone into still water, how long does a communicating civilization last? That last variable is the one that changes the emotional tenor of the equation entirely. Because the universe is old. 13.8 billion years old. And if civilizations rise and fall, if they burn bright for thousands or tens of thousands of years and then go quiet, for whatever reason, through catastrophe or transformation or a silence chosen rather than imposed, then the galaxy could be full of their remnants. Full of dead radio signals still traveling outward from planets that have long since gone dark. Full of the echoes of conversations that ended before our sun had finished forming. We may not be alone. We may simply be listening at the wrong moment, tuned to frequencies that no longer carry anything, in a universe so large that the word alone loses some of its meaning. Distance in space is not merely a matter of separation. It is a matter of time. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was, each point of light a message from the past, some of them from the very deep past, from stars that no longer exist, from light that left its source before this planet had cooled enough to hold an ocean. The star Betelgeuse, that red swollen shoulder of the constellation Orion, sits approximately 700 light-years from Earth. The light you see when you look at it left that star 700 years ago, when this planet was in the middle of the 14th century, when the Black Death was moving across Europe and the Ming dynasty had not yet risen and no human being had any concept of what a star actually was. That light has been traveling through space for all of that time, through all of that human history, arriving now, tonight, at the retina of anyone who happens to look up. And Betelgeuse is a near neighbor by cosmic standards. Andromeda, the nearest major galaxy to our own, is 2.5 million light-years away. The light from Andromeda's stars that reaches your eyes on any given night left its source 2.5 million years ago, when our ancestors were early members of the genus Homo, when stone tools were a new technology, when the ice ages were just beginning their long rhythm of advance and retreat across the northern continents. The galaxy you are looking at when you look at Andromeda is a ghost. A portrait of something that no longer exists in the form you are seeing. What Andromeda looks like right now, in this moment, is information that will not reach Earth for another 2.5 million years. This is what it means to exist inside a universe governed by a finite speed of light. The present moment, the actual simultaneous now of the cosmos, is inaccessible to us. We live inside a kind of perpetual past, surrounded by light that carries news of what was rather than what is. And the further you look, the older the news becomes, until at the very edge of the observable universe, at the boundary of what any telescope can reach, you are seeing light that left its source nearly 13.8 billion years ago, light from the early universe itself, from a time before galaxies had fully formed, before stars had completed more than a handful of generations, from a cosmos that looked nothing like the one we inhabit now. The observable universe. That word observable carries more weight than it first appears to. It does not describe the whole universe. It describes only the region from which light has had time to reach us in the 13.8 billion years since the Big Bang. Beyond that boundary, space continues. How far it continues, whether it continues forever or curves back on itself or branches into structures we have no mathematics yet to describe, is genuinely unknown. Not unknown in the sense of being difficult to measure. Unknown in the sense that the question may not be answerable from inside the universe itself, the way a character in a novel cannot read the cover of the book they inhabit. The observable universe alone contains an estimated 2 trillion galaxies. 2 trillion, each containing hundreds of billions of stars. Each of those stars potentially orbited by worlds. Each of those worlds a surface, a chemistry, a history, a set of conditions that have been running for billions of years in the dark, unobserved, unreported, existing with the same completeness and indifference to our awareness that a stone at the bottom of the ocean has, fully real and fully present and entirely unconcerned with whether anything is watching. The scale defeats imagination the way the cold defeats the body. Not through violence, but through a kind of patient overwhelming, a gradual dissolution of the frameworks the mind reaches for, until the mind simply stops reaching and rests in the enormity of what it cannot hold. There is a particular quality to that kind of vastness. It is not frightening in the way a sudden noise is frightening. It does not startle. It settles. It settles over the mind the way deep winter settles over a landscape, slowly, softly, until everything familiar is covered and the world looks like something you have never seen before, even though it is the same world it has always been. You are the same person you were before you began to think about 2 trillion galaxies. And yet something has shifted. Some internal furniture has moved. The room of your understanding is arranged differently now, and you are not entirely sure you can find your way back to the version of yourself that found the everyday world sufficiently large. This is what space does. Not through force. Through scale. Through the patient and indifferent arithmetic of distance. And distance, in space, is not merely inconvenient. It is lethal in ways that are worth sitting with slowly, because the danger of space is not the kind of danger most people picture when they hear the word. Most people imagine explosions, equipment failures, the dramatic rupture of a hull. These things are real, and they are serious, but they are not the deepest danger. The deepest danger is quieter. It is the environment itself. The vacuum, the cold, the radiation, the silence that is not merely the absence of sound, but the absence of the medium through which sound could ever travel. Space is not a place that is hostile to life the way a predator is hostile. A predator notices you. Space does not notice you. It simply is what it is, and what it is happens to be incompatible with the chemistry of living things in almost every way it is possible to measure. Begin with the cold, because the cold is the thing that asks to be felt. In the vacuum of space, far from any star, the temperature of the background environment settles at approximately 2.7 Kelvin. That number requires translation. 0 Kelvin is absolute zero, the theoretical floor of all temperature, the point at which molecular motion itself ceases, the point beyond which cold cannot go because there is nothing left to remove. 2.7 Kelvin is almost there. It is 2.7 degrees above the last warmth anything in the universe can hold. It is so cold that the word cold no longer quite applies, the way the word dark no longer quite applies to the interior of a black hole. These are conditions that exist beyond the comfortable reach of the vocabulary we built for ordinary life. That background temperature, 2.7 Kelvin, is not nothing. It is something specific and remarkable. It is the cosmic microwave background, the faint thermal afterglow of the Big Bang itself, the universe's oldest light, stretched by 13.8 billion years of cosmic expansion from brilliant gamma radiation down to a whisper of microwave energy so diffuse and so uniform that it fills all of space like a nearly perfect echo of the moment everything began. The cold of space is not empty cold. It is ancient light, cooled almost to silence. And yet, paradoxically, if you were to float in that same vacuum near enough to the sun, you would not freeze. You would roast. Because in a vacuum, there is no medium to carry heat away from you conductively. The sun's radiation would pour into you and have nowhere to go. You would accumulate energy with nowhere to release it. The human body in direct solar proximity in open space faces temperatures that can exceed 120 degrees Celsius on the sun-facing side, while the shadowed side simultaneously plunges toward the cryogenic. Space is not uniformly cold in the way a winter morning is cold. It is radically asymmetric. It is a place where the difference between light and shadow is the difference between burning and freezing, and both are happening at the same time, separated by nothing more than the thickness of your own body. This is why spacecraft are wrapped in layers of thermal insulation that seem almost excessive until you understand the environment. The spacesuits worn by astronauts on extravehicular activities are not simply pressure vessels, though they are that too. They are finely engineered thermal regulation systems, carefully balancing the absorption and reflection of solar radiation, circulating cooled water through inner layers to carry metabolic heat away from the body, maintaining the narrow band of temperature in which human biology continues to function, that small and specific range of warmth that life requires, held in place against an environment that pulls in both directions simultaneously, toward fire and toward ice, with equal and total indifference. The International Space Station, drifting in low Earth orbit at roughly 400 kilometers above the surface, experiences temperature swings of more than 250 degrees Celsius as it moves through sunlight and shadow every 45 minutes. Every 45 minutes. 16 times per day, the station passes from blazing solar exposure into the deep cold of Earth's shadow and back again. The materials that hold it together must endure this cycling without expanding and contracting themselves into failure. The engineering required to achieve this is extraordinary, and it works, and it continues to work, and yet the underlying reality it is managing is one of the more extreme thermal environments a human-made object has ever been asked to survive. And all of this is still within the relatively sheltered neighborhood of our own solar system, still bathed in the light and influence of a nearby star, still close enough to a gravity well to remain in a stable orbit, still in a region of space that is, by cosmic standards, unusually warm and eventful. Move further out, past the planets, past the scattered disk, past the Oort cloud into the genuine interstellar medium, and the environment becomes something else entirely, something quieter and more absolute, a darkness and a stillness and a cold so thorough and so complete that the concepts of warmth and activity begin to feel like rumors from another world, distant reports of conditions that exist somewhere but bear no relationship to the vast and frozen quiet in which you now drift. In the interstellar medium, the space between star systems, the density of matter drops to a few atoms per cubic centimeter. A few atoms. In the air around you right now, in the space occupied by a single cubic centimeter, roughly the volume of a sugar cube, there are approximately 27 million trillion molecules colliding and vibrating and carrying heat. In the interstellar medium, that same volume contains perhaps 3 or 4 hydrogen atoms, motionless and separate and unaware of one another in any meaningful physical sense. It is not merely empty. It is empty in a way that makes the word empty feel insufficient, the way a single candle in a cathedral at midnight is technically light, but is more accurately described as a different quality of dark. And yet, even this is not the emptiest space has to offer. Within the large-scale structure of the universe, the galaxies and galaxy clusters are not distributed evenly. They are arranged in a vast cosmic web, long filaments and sheets of matter surrounding enormous regions of almost nothing at all. These regions are called voids. The largest known void, sometimes called the Boötes void, spans approximately 330 million light-years across. A light-year is the distance light travels in a year, moving at nearly 300,000 kilometers per second without pause. 330 million of those years of distance, in every direction, containing almost nothing. No galaxies. No stars, no planets, no dust clouds gathering toward eventual collapse. Just space, extending in every direction, achingly uniform, achingly still, a volume of the universe so large that if our own Milky Way were placed at its center, we would not have known, for most of human history, that we were inside anything at all, because the nearest galaxies would be so far away that the night sky would appear almost entirely dark, stripped of the faint smear of the Milky Way's spiral arms, stripped of the distant light of neighboring galaxies, reduced to a blackness so thorough it would feel like the universe had simply ended at the edge of the observable. This is what darkness actually means on cosmic scales. Not the darkness of a room with the lights off. Not even the darkness of a clear rural night with no moon. But a darkness so fundamental that the concept of night and day loses its footing entirely, because there is no star close enough to define either. No cycle. No reference. Just the permanent and absolute dark of a region so empty that light itself passes through without leaving a mark. The cold in such a void would mirror the emptiness. Without stars to radiate energy, without the gravitational compression of matter generating heat, the temperature would settle at that same ancient floor, 2.7 Kelvin, the cosmic microwave background filling even the voids with its faint and uniform whisper, the last trace of warmth the universe inherited from its own beginning, cooling still, growing fainter still, the way the memory of a fire grows fainter in a room long after the fire has gone out, until the distinction between remembering warmth and not remembering it becomes a matter of instruments rather than experience. There is something about that image that asks to be held quietly. The universe, in its largest and most empty regions, is sustained in its faint warmth by nothing more than the echo of its own creation. The Big Bang is not only history. It is present. It is the temperature of the room. It is the 2.7 degrees that separate the universe from the absolute silence of 0 Kelvin, and it is decreasing, slowly, over timescales that make geological time feel like a breath held and released, but decreasing nonetheless, the echo fading the way all echoes fade, following the same law everything follows, moving always in the direction of greater stillness. Physicists call this direction entropy, the tendency of systems to move from ordered, energetic states toward disordered, lower-energy ones. A hot cup of coffee cooling on a table. A sandcastle dissolving in the tide. A star burning through its hydrogen and collapsing inward when the fuel is gone. These are not accidents or failures. They are the universe doing what it does, following the gradient it has always followed, from the extraordinary concentrated energy of the Big Bang toward a final state so diffuse and so cold and so uniformly spread that no further change is possible. A state cosmologists call the heat death of the universe, a name that carries a certain irony, because it describes not heat but the final and absolute absence of any temperature difference anywhere, the moment when there is no longer a warm place and a cool place, no longer any gradient for energy to flow along, no longer any process, any event, any change of any kind. That end is so far in the future it cannot be meaningfully expressed in years. The numbers involved have more digits than there are atoms in the observable universe. And yet it is the direction everything is moving. Every star that burns, every cup of coffee that cools, every breath you take and release is a small and local contribution to that long and patient unwinding, a universe slowly spreading its warmth into evenness, thinning it across distances that grow larger as space itself continues to expand, carrying galaxies apart from one another not through any force pushing them but through the stretching of the fabric in which they are embedded, the way dots drawn on the surface of a balloon move apart from one another as the balloon is inflated, not because the dots are moving but because the surface between them is growing, and there is nothing to stop it, no wall at the edge, no boundary where expansion ceases and stillness begins, just the continuous and silent unfolding of space. Into more space, distance generating distance, emptiness deepening into emptiness, the universe becoming, incrementally and without ceremony, more of what it already is. This expansion has a name. It is called the Hubble flow after Edwin Hubble, the astronomer who first measured it in the early 20th century and understood what he was seeing, that the galaxies were not simply scattered randomly in a static space but were receding, all of them, in every direction, their light stretched toward the red end of the spectrum by the very expansion of the space their light was traveling through. He was not the first to suspect it. The mathematics had been there, embedded in Einstein's equations of general relativity, but Einstein himself had resisted the conclusion, had inserted a term into his equations specifically to prevent them from implying an expanding universe, a term he later called his greatest blunder, because the expansion was real, the equations had been right, and the resistance had been a failure of imagination rather than a failure of physics. There is something worth pausing on in that moment. One of the most powerful scientific minds in human history, confronted with the implication of his own work, could not accept it. Not because the mathematics were unclear, because the conclusion was too strange. Because a universe that had a beginning and was actively expanding toward an end was not the universe he had carried in his mind. And so he adjusted the equations to match the expectation rather than adjusting the expectation to match the equations, and the universe continued expanding without his permission, indifferent to what any mind found acceptable. Space has a way of doing that, of exceeding the comfort of the frameworks brought to it, of being more than the models made to contain it. Not defiantly, not dramatically, simply by being what it is, consistently and without modification, while the minds observing it revise and reach and occasionally discover that what they thought was a boundary was actually a door. Beyond the expansion, beyond the cold and the vacuum and the scale, there is another quality of space that deserves to be considered slowly. It is the radiation. Not the dramatic Hollywood version, the green glow of science fiction, but the real and omnipresent reality of a universe filled with electromagnetic energy moving in every direction at all times, passing through everything with varying degrees of ease, some of it harmless, some of it quietly and persistently damaging to the biological machinery of living things. The Earth's magnetic field and atmosphere together form a shield. This is not a metaphor. The magnetosphere deflects charged particles streaming outward from the sun in the solar wind, bending their paths around the planet in great curving arcs that make the field lines visible only at the poles, where the particles spiral inward and collide with atmospheric gases and release that energy as light, the aurora, the green and violet and white curtains of luminescence that appear in the high latitudes on clear nights, beautiful and cold and utterly indifferent to the wonder they produce. In those who see them, the atmosphere handles the rest, absorbing ultraviolet radiation, scattering the incoming light, providing a column of air dense enough that most of the radiation reaching the surface has already been filtered to the narrow bands that living chemistry can tolerate. Remove that shield, and the exposure changes completely. Astronauts in low Earth orbit are already partially outside the protective bubble of the magnetosphere, operating in a radiation environment measurably more intense than the surface below them. Over time, this exposure accumulates. Radiation damages DNA. It does not always do so catastrophically. More often it does so gradually, in ways the body attempts to repair, successfully most of the time, until it is not. The increased cancer risk associated with long-duration spaceflight is real and measured and taken seriously by the agencies that plan such missions. It is one of the central biological challenges of any future attempt to send human beings to Mars or beyond, not a hypothetical concern but a documented physiological reality unfolding in the bodies of every astronaut who has spent extended time beyond the atmosphere. And the solar wind is not constant. The sun is not a steady lamp. It breathes. It cycles through periods of greater and lesser activity over an approximately 11-year rhythm, and within that cycle it produces sudden and violent events, solar flares, coronal mass ejections, enormous eruptions of plasma and magnetic field that can accelerate charged particles to a significant fraction of the speed of light and hurl them outward across the solar system in waves that arrive at Earth within minutes to hours of the initial eruption. On the surface, the planet's shields absorb this. In deep space, far from any protective field, an astronaut caught in a major solar particle event without adequate shielding would receive a radiation dose capable of causing acute radiation syndrome. Within hours, the body's own repair mechanisms overwhelmed by the sheer quantity of damage arriving faster than they can address it, a storm not of wind and water but of invisible energy moving at velocities that make weather seem quaint, arriving without sound, without color, without any sensory warning at all, detectable only by instruments, perceptible to the body only in its aftermath, when the damage has already been done and the cells are already struggling with what they have been asked to absorb. This is one of the reasons a journey to Mars is so much more complex than the distance alone suggests. The distance is already staggering, between 54 million and 400 million kilometers depending on where the two planets are in their respective orbits, a range that itself speaks to the dynamic and constantly shifting geometry of the solar system, nothing fixed, nothing static, every body in continuous motion relative to every other body. The whole system a slowly turning and mutually influencing arrangement of masses following paths that are predictable but never simple. At closest approach, a one-way journey to Mars using current propulsion technology would take approximately 7 months. 7 months in a spacecraft, moving through a radiation environment with no planetary magnetosphere overhead, no thick column of atmosphere to filter the incoming energy, just the hull of the vessel and whatever shielding its designers were able to include without making the craft too heavy to launch. And during those 7 months, the body does other things as well, things that have nothing to do with radiation and everything to do with the absence of gravity. In microgravity, the human body begins to change. Not slowly. Immediately. The fluid that normally pools in the lower body due to gravity redistributes upward, toward the head and chest, producing a persistent sensation of congestion, a fullness in the face that astronauts describe as similar to hanging upside down, except that it never goes away because there is no right side up to return to. The heart, which is accustomed to working against gravity to push blood upward, finds itself in an environment where that effort is unnecessary and begins to adapt, becoming slightly smaller and less efficient in ways that take time to reverse after return to Earth. The bones, which maintain their density through the mechanical stress of bearing weight, begin to lose mass at a rate of roughly 1 to 2% per month in microgravity, because the stress that signals the body to maintain bone tissue is no longer present, and the body, being efficient in the way all biological systems are efficient, stops investing resources in structures that do not appear to be needed. The muscles follow the same logic. Without the constant low-level effort of supporting the body against gravity, they atrophy. Astronauts on the International Space Station exercise for approximately 2 hours every day specifically to slow this process, using resistance equipment designed for the purpose, and still return to Earth after 6 months requiring assistance to walk, their legs having partially forgotten what walking demands. The vestibular system, the inner ear's apparatus for sensing orientation and motion, becomes confused in microgravity and takes time to recalibrate. Vision changes too, in ways that were not fully understood until relatively recently, when imaging studies of returning astronauts revealed that the pressure of redistributed fluid was deforming the eyeball, flattening the back of the eye against the optic nerve in ways that altered visual acuity and raised concerns about permanent damage to vision in astronauts who spent very long periods in space. The body is designed for Earth. It is the product of billions of years of evolution in a specific gravitational field, under a specific atmospheric pressure, bathed in a specific spectrum of radiation filtered by a specific magnetosphere and a specific column of air. Remove any of those conditions and the body begins, quietly and without drama, to become confused about what it is supposed to be doing. It is not fragile in the ordinary sense. It is extraordinarily resilient. But its resilience is calibrated to a particular world, and space is not that world. Space is the absence of nearly every condition that world provides, offered in exchange only for the cold and the vacuum and the radiation and the silence and the distances that the mind releases rather than comprehends. There is a term used in human spaceflight research, the phrase acceptable risk, and it does a great deal of work in a very small space. Every mission beyond the atmosphere involves a careful and ongoing negotiation with acceptable risk, the acknowledgement that the environment cannot be made safe, only managed, only partially mitigated, only approached with the best available engineering and medicine and planning, and then, ultimately, accepted as the condition under which the work must be done. The astronauts who go know this. They have read the studies and understood the probabilities and made their peace with a set of odds that would give most people pause, not because they are reckless but because they have decided that whatever lies beyond the atmosphere is worth the cost of reaching it, and that decision, made quietly and with full information, is one of the more remarkable things a human being can do. Because the pull of space is real, even knowing what space is. Knowing the cold and the vacuum and the radiation and the biological cost and the distances that swallow light for millions of years before releasing it, knowing all of it, the pull remains. Something in the human mind turns toward the dark the way a plant turns toward light, not because the dark is safe or welcoming, but because it is there, because it is vast, because it contains within its silence and its cold a kind of question that the mind cannot quite stop answering. There is a term used in human spaceflight research, the phrase acceptable risk, and it does a great deal of work in a very small space. Every mission beyond the atmosphere involves a careful and ongoing negotiation with acceptable risk, the acknowledgement that the environment cannot be made safe, only managed, only partially mitigated, only approached with the best available engineering and medicine and planning, and then, ultimately, accepted as the condition under which the work must be done. The astronauts who go know this. They have read the studies and understood the probabilities and made their peace with a set of odds that would give most people pause, not because they are reckless, but because they have decided that whatever lies beyond the atmosphere is worth the cost of reaching it, and that decision, made quietly and with full information, is one of the more remarkable things a human being can do. Because the pull of space is real, even knowing what space is. Knowing the cold and the vacuum and the radiation and the biological cost and the distances that swallow light for millions of years before releasing it, knowing all of it, the pull remains. Something in the human mind turns toward the dark the way a plant turns toward light, not because the dark is safe or welcoming, but because it is there, because it is vast, because it contains within its silence and its cold a kind of question that the mind cannot quite lay down, cannot quite release. The question does not have a name exactly, but it lives somewhere beneath language, in the part of consciousness that existed before words were invented for it, the part that looked up at a dark sky 10,000 years ago and felt the same pull that a physicist feels today standing beside a launch pad in the early hours before dawn, watching fuel vapor drift off a rocket in the cold Florida air. The question is not what is out there, though that is part of it. The question is something more like, what does it mean that we are here, inside all of this, inside a universe so large and so old and so indifferent to our presence that the very fact of our asking seems almost impossible, almost miraculous, almost worth everything it costs. And space will cost you everything if you are not careful, and sometimes even when you are. The cold alone should give you pause. Not the cold of a winter morning or the cold of high altitude or even the cold of the deepest ocean trench, but a cold so complete and so ancient that the word cold begins to feel inadequate beside it. In the shadow regions of deep space, far from any star, the temperature drops to approximately 2.7 degrees above absolute zero. That number is worth sitting with for a moment. Absolute zero is the point at which all molecular motion ceases, the point at which the atoms of a substance have surrendered even the last trembling of kinetic energy, where matter becomes as still as matter can become. 2.7 degrees above that threshold is not far above it. It is very nearly nothing. And that is the temperature of the universe itself in its darkest and most empty regions, a temperature left over from the first light that ever existed, a faint thermal echo of the Big Bang still radiating outward after nearly 14 billion years, slowly cooling, slowly approaching the floor. When you float in space without the protection of a spacecraft, exposed to that environment on the sunlit side of your orbit, you will first overheat rather than freeze, because in vacuum there is no medium through which heat can convect away from you. Radiation is the only mechanism available, and radiation works slowly. But in shadow, the calculation reverses. The cold presses in not with the aggressive chill of wind, but with a quiet and total withdrawal, an absence of warmth so thorough that it feels like the universe is simply taking back what it lent you. Spacecraft must be engineered to manage this paradox simultaneously, to radiate excess heat on one side while insulating against absolute cold on the other, to keep a narrow band of survivable temperature inside a shell surrounded by conditions that would kill a human being in minutes. The suits that astronauts wear during extravehicular activity, during those long slow walks through the void above the Earth, are essentially personal spacecraft. They maintain pressure. They supply oxygen. They regulate temperature across a range that swings from roughly 250 degrees Fahrenheit in direct sunlight to nearly 250 degrees below in full shadow, a 500-degree range across which a human body must remain alive and functional. The engineering required to achieve this is extraordinary. The margin for error is almost non-existent. A single seal failure, a single valve malfunction, and the suit that stood between the astronaut and the vacuum becomes simply a very expensive garment with nowhere to be. And yet they go. And yet the suits are worn and the airlocks are opened, and the humans step out into the nothing and do their work, floating above an atmosphere that most people will never leave, suspended between the warmth of a planet they can see curving below them and the cold of a universe that extends in every direction without limit. They go because the work requires it. They go because there are instruments to repair and experiments to retrieve and structures to build that cannot be built any other way. They go because someone has to, and because the ones who do have accepted the terms of the arrangement, the terms that say you will be very small and very exposed and very dependent on the engineering and training and luck that brought you here, and in exchange you will see something that almost no one has ever seen, which is the Earth from the outside, the Earth as a object rather than a place, the Earth as a thing that exists inside space rather than a thing that space exists inside of, and that inversion, that sudden reversal of inside and out, is said to change something in the people who experience it in a way that does not fully reverse when they return. There is a name for it: the overview effect. It was coined by the writer Frank White in 1987 after he interviewed astronauts and began to notice a pattern in the way they described the experience of seeing the Earth from orbit, a pattern of quiet transformation, of perspective that widened past the point where it could be narrowed again. The astronauts described looking down at the planet and feeling the borders dissolve, not metaphorically but almost visually, the lines that human beings had drawn across the surface of the world becoming invisible from a sufficient altitude, the divisions of nation and territory and ownership simply absent from the view, replaced by the curve of a coastline, the slow spiral of a weather system, the particular blue of an ocean catching the light of a sun that was also, from up there, a different kind of object, brighter and harder and more ancient-looking than it appears from beneath the atmosphere that softens it. That blue. It deserves its own kind of attention. The Earth from space is almost shockingly blue, more blue than you expect even when you have seen the photographs, because the photographs do not fully prepare you for the context in which that blue appears, which is the absolute black of the surrounding void. There is no gradation. There is no horizon of space that fades from blue to dark the way an earthly sky fades from daylight to dusk. There is simply the planet, luminous and curved and impossibly fragile-looking, and then the black, immediate and total, and the contrast between those two things is reportedly one of the most affecting visual experiences a human being can have, a contrast that lodges itself somewhere deeper than memory and refuses to leave. And floating in that black, between the blue and the dark, you would feel the cold not as a temperature but as a presence, as a condition of the universe that was always there, underneath the warmth that stars and planets generate, waiting at the edges of every heated thing. The warmth that you have always known, the warmth of a room and a body and a sun-warmed window in the afternoon, all of it is local. All of it is borrowed from the slow burning of nuclear fires that will one day end. The cold is the default. The cold is what the universe returns to when the fire is done, and in the deep between the stars it has already returned, already settled into that long and patient stillness, 2.7 degrees above the floor, drifting outward, cooling by fractions across timescales that have no name in any human language. The stars you would see from that vantage, from outside the atmosphere, would not twinkle. This is one of the quieter revelations of orbit, a small thing set beside the immensity of everything else, but it carries a strange weight. Stars twinkle from the ground because the atmosphere bends their light, refracts it through layers of air at different temperatures and densities, creating the gentle flickering that human beings have watched for as long as there have been human beings watching anything. Remove the atmosphere and the stars become steady. They become fixed points of light rather than trembling ones, harder and more precise, more like what they actually are, which is other suns, remote and enormous and burning at temperatures the human mind was not built to hold as a concrete image. They become, in their stillness, more strange rather than less. The familiar shimmer is gone, and what remains is the thing the shimmer was obscuring, which is a sky full of nuclear furnaces separated by distances that make the word distance feel like a modest and insufficient term. The nearest of those furnaces beyond our own is Proxima Centauri, a small red dwarf star sitting approximately 4.2 light-years from the Sun. 4.2 light-years means that the light you would see from it tonight left its surface 4 years and roughly 2 months ago, traveling at the fastest speed the universe permits, across a distance of approximately 25 trillion miles, to arrive at your eye in this moment. 25 trillion miles is the nearest star. The nearest one. The first step on a staircase that continues outward past all useful analogy, past the capacity of human number systems to hold without abstraction, past the edges of the observable universe into regions that we cannot see because the light from there has not yet had time to reach us, because the universe is not old enough yet for that light to have made the journey, because we are, in this sense, living inside a bubble of visibility surrounded by an unknown that is not unknown because it is. Hidden but because the speed of light and the age of everything have conspired to place it beyond our reach, at least for now, at least for this early and uncertain moment in the life of a species that has only just begun to look up and wonder what looking up might eventually mean. We are young in the way that a species can be young, which is to say profoundly, almost embarrassingly young, a thin new layer of awareness spread across the surface of a middle-aged planet orbiting a middle-aged star in a galaxy that was already billions of years old before the solar system condensed from its cloud of gas and dust and began the long, slow process of becoming somewhere that something could live. And yet here the awareness is. Here it is, asking questions in the dark, building instruments to extend its senses past the limits of its biology, sending small metal objects outward into the cold to carry measurements back across the distances that separate us from the rest of what exists. There is something in this that resists easy description, something that sits between humility and astonishment and refuses to resolve into either one completely. The universe did not require us to understand it. The laws of physics operated for billions of years before there was anything to observe them, before there was anything to name them, before there was anything to feel the particular quality of wonder that arises when a mind encounters something vastly larger than itself and finds, in that encounter, not only fear but also a kind of reverence that has no adequate object except the thing itself. The cold of space is part of that reverence. It sounds strange to say so, but there is something in knowing the temperature of the void, in knowing that 2.7 Kelvin is the background hum of the universe, the thermal afterglow of its own beginning, that produces a feeling not unlike what people describe when they speak of the sacred. Not because the universe is sacred in any religious sense, but because the universe is so entirely itself, so complete in its indifference, so vast in its patience, that standing at the edge of knowing it produces in the mind a stillness that resembles, at least in its texture, the stillness that comes from being in the presence of something that cannot be measured by the usual instruments of human importance. Space does not care about importance. This is one of its most clarifying qualities, and also one of its most unsettling ones. The radiation that crosses the void does not distinguish between what matters and what does not. The cold presses equally against the hull of a spacecraft carrying experiments that may advance human medicine by decades, and the hull of a craft carrying nothing at all. The micrometeorites that drift through the solar system at tens of thousands of miles per hour do not slow for significance. They move as they have always moved, along the paths that gravity and momentum have assigned them, indifferent to everything, ancient and unhurried and precise in the way that only things without intention can be truly precise. And the distances keep asserting themselves, keep returning to the foreground of any honest account of what space is. Light, moving at approximately 186,000 miles per second, takes 8 minutes and 20 seconds to travel from the surface of the Sun to the surface of the Earth. That same light takes about 43 minutes to reach Jupiter at its average distance. It takes over 5 hours to reach the edge of the solar system near Pluto. And then it keeps going into the interstellar medium, the thin and cold region between the stars, where the density of matter drops to almost nothing and the temperature approaches that universal floor, and it travels for 4 years before it reaches another star, and then it keeps going, past stars and nebulae and the slow pinwheel structures of other solar systems, for 100,000 years before it crosses the diameter of our own galaxy, and then it keeps going for 2.5 million years before it reaches the Andromeda Galaxy, our nearest large galactic neighbor, a spiral of roughly 1 trillion stars suspended in the dark at a distance that the mind can state as a number but cannot genuinely hold as a distance, cannot feel as a separation the way you feel the distance between yourself and a far hillside or a ship on the horizon. The Andromeda Galaxy is approaching us, incidentally. It and the Milky Way are drawn toward each other by the mutual gravity of their combined mass, closing the distance between them at roughly 110 kilometers per second, which sounds fast until you consider that the distance they are closing is 2.5 million light-years, and that the collision, if collision is even the right word for what happens when two structures that are mostly empty space interpenetrate each other over hundreds of millions of years, is not expected to occur for approximately 4.5 billion years, which is, coincidentally, roughly the remaining lifespan of the Sun, which means that the Earth, if it still exists, will be watching the sky slowly fill with the stars of another galaxy at approximately the same time that its own star begins to exhaust its hydrogen fuel and swell into the red giant phase that will eventually consume the inner planets. These timescales do something to the mind when you allow them to settle. They do not crush it, exactly, though there is a weight to them. They do something more like dissolve it, gently and without violence, the way salt dissolves in warm water, losing its edges, spreading into the larger medium until the boundary between the self and the surrounding becomes harder to locate, harder to insist upon. This is not an unpleasant feeling, at least not entirely. There is something in the dissolution that carries its own quiet comfort, something in the reminder that the self is not the measure of things, that the universe was not assembled around the requirements of human consciousness and does not depend upon human consciousness to continue, that whatever we are participants in something that began long before us and will continue long after, something so large and so old that our presence within it, brief and small as it is, carries a kind of weight precisely because of how unlikely it seems. The improbability of awareness is one of the stranger facts that space forces into view. For the universe to produce a mind capable of contemplating the universe required an extraordinary sequence of events, each dependent on the one before it, each balanced on conditions that could have resolved differently at any point. The precise ratio of matter to antimatter in the first moments after the Big Bang. The particular rate at which the universe expanded, fast enough to prevent immediate gravitational collapse, but slow enough to allow matter to clump into galaxies and stars. The nuclear physics of stellar interiors that fuses hydrogen into helium and helium into carbon and carbon into oxygen and all the heavier elements without which chemistry and biology are simply not possible. The supernova explosions that scatter those elements into the surrounding gas clouds. The formation of a solar system with the right kind of star, stable and long-lived, burning steadily enough to allow billions of years of planetary evolution. The presence of a large planet like Jupiter in the outer solar system, whose gravity deflects many of the comets and asteroids that would otherwise sterilize the inner planets on a regular basis. The existence of a large moon, stabilizing the axial tilt of the Earth and moderating the climate over geological time. The liquid water. The magnetic field. The ozone layer. The particular sequence of chemical accidents that produced the first self-replicating molecule in some warm and mineral-rich pocket of early ocean. Every one of these conditions had to hold. Every one of them did. And the result, after 4.5 billion years of biological experimentation and extinction and adaptation, is a creature capable of standing on the surface of the planet that produced it and looking outward into the dark and understanding, at least partially, what it is looking at. Understanding the nuclear physics of the stars it sees. Understanding the geometry of the orbits of the planets. Understanding the expansion of the universe and the temperature of the void and the age of the light arriving from distant galaxies. Understanding, in other words, not just that the universe is there, but something of how it works, something of the rules by which it operates, and finding in those rules a beauty that is not decorative but structural, a beauty that lives in the equations themselves, in the way that a small number of elegant principles gives rise to the full complexity of everything that exists. This is what space holds, beyond the cold and the vacuum and the radiation and the silence. It holds the context for everything. It holds the frame within which the earth makes sense, within which life makes sense, within which the brief and luminous fact of consciousness makes sense, or at least makes a different kind of sense than it makes when you are standing inside it without looking up. The overview effect that astronauts describe is not only about seeing the earth from the outside. It is about understanding, viscerally and suddenly and with the full weight of direct experience, that the outside exists. That there is a frame. That the world you have always inhabited is not the extent of what is real, but only a small and precious and extraordinarily fortunate corner of a much larger and mostly inhospitable reality. And that corner is worth protecting. This is something that comes through clearly in the accounts of people who have been to space and returned, who have seen the atmosphere from above and understood, in a way that no photograph fully conveys, how thin it is. How genuinely, terrifyingly thin the layer of air that makes the Earth habitable actually is. From the surface, it feels inexhaustible. It feels like the sky goes on forever, because from the inside the gradient is gradual, the blue deepening and thinning so slowly that the transition from livable to lethal is invisible to the naked eye. But from orbit, the atmosphere appears as what it is, which is a membrane, a thin blue line curving against the black, so delicate in proportion to the planet it encloses that astronauts consistently describe a feeling of protectiveness when they see it, a feeling that something fragile is being held in place by conditions that are not guaranteed, that the warmth and the moisture and the breathable air that make the surface of this planet so improbably welcoming are not features of the universe, but exceptions within it, local and temporary and worthy of a care that is difficult to feel fully from the inside. From the inside, the atmosphere is simply the sky. From the outside, it is the only thing standing between everything you have ever known and the cold that waits without patience or malice or any quality at all, because the cold of space is not cruel, it is simply the absence of warmth, and absence does not need a disposition. It simply is. It simply persists, at 2.7 degrees above the floor of all possible temperature, in every direction, across every distance, through every silence that the universe has accumulated over nearly 14 billion years of expansion and cooling and the slow rearrangement of matter into forms that briefly burn and then go dark. And knowing that, feeling the weight of it settle into the mind, the way the mind allows certain truths to settle when it is quiet enough and still enough to receive them, something shifts. Not dramatically. Not with the force of revelation or the brightness of sudden understanding. But quietly, the way the quality of light shifts in a room when the sun moves behind a cloud, a change you notice not when it happens but a moment after, when you look up and find that everything looks slightly different than it did and you cannot say exactly when the change occurred. What shifts is the sense of scale. Not the intellectual understanding of scale, which can be achieved by reading numbers in a book, but the felt sense of it, the embodied awareness that the place you occupy in the universe is very small and very specific and very dependent on a set of conditions that the universe did not arrange for your benefit but that you have the extraordinary luck of inhabiting regardless. The Earth is not the center. The Sun is not the center. The galaxy is not the center. There is no center, or rather every point is equally central to its own experience of the whole, which amounts to the same thing. You are here, and here is somewhere, and somewhere, in a universe this large, is already more than probability would seem to promise. The astronauts come back carrying this. They come back changed in ways they sometimes struggle to articulate, not because the experience was beyond language, but because language was built for a world that fits inside the atmosphere, and the things they have seen and felt exist outside of it, in a register that the vocabulary of daily life was not designed to hold. They speak of the silence, though of course space itself made no sound for them to hear. They speak of the feeling of smallness, though their bodies occupied the same volume they always had. They speak of beauty, which is perhaps the closest available word for whatever it is that happens when a human mind encounters something so far beyond its ordinary scale of reference that the usual categories of experience temporarily dissolve and something older and quieter rises in their place. That older, quieter thing is what this narration has been circling, in its slow way, through all the facts and distances and temperatures and biological costs. It is the thing that makes space not only dangerous but also, in its way, sacred. Not sacred in the sense that any particular tradition would claim it, but sacred in the older sense of the word, which is simply set apart, which is simply other, which is simply beyond the ordinary and deserving of a quality of attention that ordinary things do not require. Space asks for that attention. It earns it by being what it is, which is the context of everything, the darkness against which all light is defined, the cold against which all warmth is felt, the silence against which every sound that has ever been made on this planet registers as a kind of miracle, a brief and local and improbable eruption of complexity in a universe that is mostly emptiness and mostly cold and mostly very, very old. And you are here, inside the warmth, inside the thin blue membrane, inside the noise and the light and the movement of a world that is, by every cosmic measure, an anomaly, a deviation from the mean, a place where the numbers happen to come out right and matter organized itself into shapes that could breathe and think and look up at the dark and feel something that cannot quite be named but that has been felt, in some form, by every human being who has ever lived beneath an open sky on a clear night and wondered what all of it means and whether the wondering itself means something. It may mean something that the universe produced, in this small corner, in this thin warm layer of a medium-sized planet, creatures capable of knowing where they are, capable of measuring the cold and calculating the distances and sending instruments into the void to return with data that extends the reach of knowing past the limits of biology, capable of sitting quietly in the dark and letting the facts of the cosmos settle into them like starlight settling into a still lake, slowly, without disturbance, illuminating nothing dramatically but changing, by its presence, the quality of the dark. Let the dark be what it is tonight. Let the cold of it, 2.7 degrees above the absolute floor, exist at the edges of your awareness without pressing too close. Let the distances extend outward in every direction past the reach of any number you have been given. Let the stars be what they are, other suns, ancient and burning and so far away that the light arriving from them now is older than anything you have ever touched. Let all of it be there, enormous and silent and indifferent and, in its own way, very beautiful. And let yourself be here, small and warm and breathing.